Hello students, I'm Dr. JAYASRI. Today I'm going to deal about the minimum cost spanning tree by using the Prim's algorithm. In the last class we have discussed about the merge sort, and today we'll go about the minimum cost spanning tree. So what do you mean by spanning tree? Actually we need to learn about the tree structure we know about and spanning tree. So a spanning tree is defined like a subgraph, and it will be connected, and we can use like a directed and undirected graphs also, and it should be like weighted. And here the spanning tree is a process where we include all the vertices, that particular subgraph, and we use n vertices and n-1 edges. All right, so and the tree should be like acyclic. It should not be in the cyclic format. Whatever we can use, that it should not be in the cyclic format. Okay, so when every node in the graph is a part of a tree, so each and every node is a part of a tree. So here we go with the example that the minimum cost spanning tree for the directed graph is that we have all the properties of the spanning tree which are added, and if we have a constraint about the weights, particular weights. So what type of weight we need to take? As the name implies that the minimum cost spanning tree. So we need to find the minimum cost here regarding the spanning trees here. All right. So, and we have like many possible MSTs, minimum cost spanning tree possible ways we have. Here we'll go with an example like the 1 and 2, 3. We have like 3 nodes, and this is like the directed graph, and we have some weighted edges. This is a weight, all right, and this is a directed graph, and we have some weights here. So in this we need to find out the minimum cost spanning tree. How the minimum cost spanning tree we need to move on. So as I told that it should be like n vertices and n-1 vertices, edges, n-1 edges. So here we have like 1 we have connected, and 2 we have connected, and 3 we have connected. So we have here all the methods, and we have not connected here because it should be like acyclic. It should not be in the cyclic format. All right. So that's why we have taken here. So this is an example. And we have like some properties of the spanning tree. The spanning tree holds all these different types of principles that we need to follow. First, vertices in the graph, as we have already shown that. And next we have like a number of 1-1 edges we have. And the tree spanning should not be disconnected. It should not be disconnected. It has to be tree-like structure. And it should be like what? Acyclic. All right. A cyclic form should not be there. And the total cost weight, you need to find out the minimum cost spanning tree. So we can have a many number of possible ways for a particular graph. For example, if you want to check like we have A node, B node, C node, and D node. 4 possible. This is a 4 connected vertices we have. Here, what we are going to do that, we need to frame like, first we need to connect A to B, and next B to C, and next, this is one possible way. So if we connect here, this is the total graph connecting with vertices, comma, edges. Graph is equals to. So this is one possible way. And next possible way, A is connected to B, and A is connected to D, and D is connected to C. This is next possible way. And next, A connected to D, connected to C, and connected to B. Here we have leftover. This is a third possible way. All right. And next, A is connected. Now B is connected. D to C already we have given. D to C is already given. And D we have. So this is the next possible way. All right, the 4 possible ways. So here we have connected. B we have not connected. D we have not connected. Yes. So this is the 4th possible way. So we have all the 4 possible ways for MST, minimum cost spanning tree. So these are all the properties that we have checked out. All right. And next, what is the definition of the spanning tree? So a minimum cost spanning tree is defined as a spanning tree that has the minimum weights among all the spanning trees. So the minimum tree has all the properties of the spanning tree, which is added constraint minimum possible weights we need to take. And then also we need to check it out this particular example. So this is what the minimum cost spanning tree among all the spanning tree, and we need to find out the minimum cost, like whatever the cost we have, we need to calculate overall that cost, and you have to write here the cost. That will be understood by taking of the two examples. One, the spanning tree examples which we are going to take, that one is for Prim's algorithm and next one is for Kruskal's algorithm. So algorithms to find the minimum cost spanning trees, we will use two algorithms. What are those? One is with Prim's and next one is Kruskal's algorithm. In today's class, we'll see about the Prim's algorithm. All right. Now we are moving on to the Prim's minimal spanning tree algorithm. So what is the Prim's minimum spanning tree? It's one of the efficient methods. One of the efficient methods to find the minimum cost spanning tree. So in the particular given graph, subgraphs, it should be like weighted, connected, undirected. So this is possible for the Prim's minimal cost spanning tree. It's a subgraph as we have discussed in the previous session of minimum. All the vertices present in the main graph with the least possible edges with the minimum cost. That was we have discussed. And it can use the similar shortest way algorithm also. And we need to path the root of all the vertices. We need to cross each check of all the vertices and least cost adjacent edges we need to take. And at last we need to find the total cost. So how much total cost? And it should not be cyclic. Cyclic you shouldn't maintain, and we have to consider all the vertices and nodes and connected and -1 and all that we need to check it out in this particular minimum cost Prim's algorithm. So we'll go with an example. First we need to check it out. A small example regarding that, the Prim's algorithm. So how you need to execute the Prim's algorithm? The inputs taken by the algorithm and the graph will be graph we have. As I told, graph we have the vertices and edges. V is called as an vertices and E is called as an edges as a source vertex. So here in this particular example, we have to start at the source vertex. So the starting vertex we have given is A, and A is directed to B directly. So this is a directed graph. And B is connected to C, C is connected to D, and D is both connected. So from E to D we can take and D to A we can take. So in this, which is the minimum, when we are doing the problem, that we can check it out. And here also E to F, again it is connected both sides. So again E to F. So in this all the weighted, this is a weighted we have given, and it should be cyclic. All right, it has a cyclic. And we have to maintain all the total cost path. Total cost path, how much we have to check it out in this particular example. This is a small example. And next we need to move an algorithm when we are doing the problem, that is main and must. So algorithm. Once array has been visited, it has been stored the word vertices finally first root. From the first root we need to start the problem, and after solving the problem it has to be moved to the next arbitrary root as yes is a visited array. So when it is visited, and we need to check it out the minimum cost, and we have to forward with the next process. Check whether the adjacent vertices is last visited vertex and the present visited vertex array is not. Yes, you have to check the adjacent vertices and the last visited vertex are present or not. This is a main point. If the vertices are not in the visited array, then you have to compare the edges and the least cost. You have to compare the edges and you have to compare the least cost. So what is the cost? As we are examples, we are learning from the minimum cost spanning tree. So this is the comparison of the least cost, and output spanning tree will be the different by comparing all the least cost methods. So adjacent unvisited vertex is the least cost added to the visited vertex. This again unvisited vertex will be added least cost visited object, and the least cost is added to the minimum cost. Again, the new tree is going to be added to the next process, and from that process it will be the main route, and it has to be continued for the next step. So step 2 and 4 are repeated for all the unvisited graphs. If it is not visited, again we need to move on until all the edges will be reaches, and it should not be frame cycle. So calculate the minimum cost spanning tree. So the Prim's algorithms, we have like real-time applications also, where we are going to use the different real-time applications. One is with the minimum cost networks connecting computer servers, also routers also we can use that. And all nodes will be connected to the least cable length or cost. For this purpose also we can use the real-time examples as a minimum. Prim's, Kruskal's algorithms and all that. So connecting power stations, substations and transformers. So wiring while maintaining the fully connectivity or not, we can use by using this Prim's algorithm. And you can form the minimum cost spanning tree in clustering. So where all the groups we can find and we make it as one cluster, and broadcasting. So from one sender to so many of receivers when we want to take, and that receivers will be using for different types of applications. These are all the real-time applications we can use the Prims. And now we are moving on to the example. So find the minimum spanning tree using Prim's method. Now we have a greedy approach for the given graph. So S is an arbitrary root. So they have given the S is the starting. This is an undirected, and it is connected, and it is weighted. So we have all the possible connections, and we have 1, 2, 3, 4, 5, 6. 6 nodes we have. All right. So we need to make it as a concept where we need to check it out, the Prim's algorithm in detail with 1-to-1. All right. So from S to A. So in this minimum cost spanning tree, we need to take then all that particular points, and here also Prim's algorithm points together, and we have to construct a new minimum cost spanning tree. All right. So we have the starting vertex is what? Yes. So yes, from yes we have 2 connections. From yes to A we have connection, and from yes to B we have connection. So in this, which one is minimum? 8. So 8 is minimum. So we have to give connection. The node starts from yes to B. So see here, the solution, step 1, create a visited, store all the vertices into that, and this will be the empty as we are starting that. So the arbitrary root is mentioned with what? Yes. So all the remaining edges that are connected to the least cost edge. So S we have like 2 connections. One is with S to A, and next one is yes to B. In this minimum 8. So that's why we have taken from yes to B is what? 8. So yes to B is 8, and visited is what? Yes and B that has been visited. So this is called the step 1 procedure. Step 2. Now which one is visitor? Now this B. The B is a new arbitrary root. Now B is the last visited, means S to B that we have taken. From B we have to check the least cost edge that is connected to the vertex B. So the vertex B, what we are going to connect it. So here B. So for B, B to S one it is connected as this is undirected graph. And next one B to A it is connected. And next is what? B to C is connected, and next is what? B to E is connected. In this, which one is shortest? So B to A is shortest. So this you need to connect now. So B to A. We have connected one, and next is what? B to A we have connected. So B to A is there, B to C is there, B to E is there, as already we have visited. So that's why we have not written here. So B to A, B to A, B to C, B to E. B to A, B to C, B to E. 9, 16. In this, 9 is shorter. So that's why we have framed that. And here B to A is the edge that is added to the spanning tree. Visited nodes will be yes, B, A. Now yes to B, B to A. Alright, this is a second step. Now we are moving on to A node now. So A. Now this is the new node. This completed. Now A to B is there, A to S is there, A to E is there, A to C is there. So we have to check here, already it is completed. So we have to check like A to S, A to C, and A to E. So this is now the step 3 we have entered. So since A is the last visitor, check the least cost. We have checked already the least cost. A to C is 22, A to B is 9, and A to E is 11. A to C is 22, A to E is 11. That is. So in this, which one is least? So 11 is least. Why? Because A to B is already there. So next visited route that we have to move is what? A to E. So but AB is already, and check whether the next least cost is added to the spanning tree or not. So that's why we have added to the spanning tree, and now the visited nodes will be S, B, A, E. Yes to B, B to A to E. So this, the third step is also completed now. Now the next we have to check is what? E. Now A to E we have taken out, which is the least cost. All right. Now E will be the next procedure. So E to B is there, and E to C is there, and E to D is there. The 3 possible ways we have. And again, we need to check in this which one is the least cost. Step 4. So already that is visited. So that's why we have taken here 2. So last visited, check the least cost vertex. E to C 18, E to D is. So that's why we will be taking here the shortest. That is E to D. So is added to the spanning tree, and next visited nodes, yes to A, yes to B, A, E, and D. So these are all we have entered. So step 4 is also completed. Now we are moving on to the D. So again, we will go to that. So we have reached the last point. So we have reached the last point. And what connections we have in this particular D? Again, we need to check. So this is the last vertex that we have visited. And we have like D to E and next D to C. So the not visited is what? D to C. And next this is already visited. So that's why we need to check it out with this C. So we have completed here. S, B, A, E, D, C. So these are all the minimum cost spanning tree that has visited once. All right, it is not been repeated. And least cost edges we have taken out. And D to 15 into this. So that's why it has been considered this one. Already it has been visited and we have added to the spanning tree. And the visited nodes are S, B, A, E, D, C. All right. So the minimum cost spanning tree we need to add like 8 plus 9 plus 11 plus 3 plus 15. All right. So 11, 20, 28, so 46. So this is your least cost minimum cost spanning tree by using Prim's algorithm. So this is a question you can solve for the next procedure. I didn't given any of the diagrammatic. You have to take it out. I have given the vertices and I have given the edges and I have given the weights. So create by yourself diagram by seeing all this and calculate the least cost minimum cost spanning tree by using Prim's algorithm. All right. Thank you.